Consider the graph f of x equals x cubed. Now, you should know what this looks like. This is the classic cubic function. It goes something like this. Okay, now what we're going to do, we're going to take the derivative and set it equal to 0. So we say f prime of x equals 3x squared, and we set that equal to 0, and then we get x equals 0. So what we have is a critical point at x equals 0. But if you look at this curve, it is clearly not a minimum or a maximum. So what in fact is it? Well, let's look at it carefully. So let's try this. Let's take the second derivative, and let's do f double prime of x, and then we get 6x. Now, if we do f double prime of x, okay, recall that f double prime gives us the concavity, and we set this equal to 0, we also get x equals 0. And whenever you set f double prime of x equals to 0 and you solve, that is a point of inflection, and that is where the concavity changes. So it goes from concave down to concave up. Now when you're doing a first derivative test, okay, and you're looking for critical points, what would happen here? What would happen is you have 0 as a critical point, and then you look to the left and right. Okay, so we're right here. Okay, well, if you plug in a positive value, say 1, you get a positive, so you get a plus, indicating that the derivatives are positive to the right of 0. And if you look to the left, you put in a negative 1, you know, negative 1 squared is positive 1, 3 times 1 is 3, you also get a plus. Okay, so this is the first derivative test. So when you're doing the first derivative test, what happens is, okay, maybe we should write this. This is our f prime test. No change, that means it's not a minimum or a maximum. And if we do our second derivative test, okay, we also got 0, but now we're looking at a different function. We're looking at 6x. 1, positive, okay, that's concave up. And to the left, we would have like a negative 1, saying that would give us a negative 6, which is a negative. And so there is a clear change in the second derivative going from concave down to concave up, as you see in the graph, and those are classically points of inflection. That's the second derivative test for points of inflection. So you do have to be careful. Now, we can use all of this calculus to basically graph things. And it can definitely help us. And so let's look at a couple of examples. Let's construct graphs. Okay, so let's start with the following. Let's start with example, how about f of x equals, let's go with 4x cubed minus 2x to the 4th. Now, a couple words are in order. So, in this day and age, if anybody needs to produce a graph of this function, everybody is going to use a computer or a graphing calculator. Okay? So previously, before the invention of those technologies, lots of graphs were constructed by hand, and calculus was an invaluable tool for that. In this day and age, the graphing of functions using calculus is still taught, but there's not as great of an emphasis due to the technologies that are available. However, it is worth exploring as a student, so that what it's going to do, calculus will help you learn more about the function itself, and you'll actually get better at calculus by working with some of these graphs, having to take the derivatives, and then figuring out the differences between, say, f prime type critical points and f double prime critical points. Maxima or minima or neither for f prime, and points of inflection for f double prime. So really good exercises. And so basically, to graph this, what we're going to do is we're going to use all of the calculus tools that we have in terms of taking derivatives and second derivatives, and then we'll look at what else we need to kind of put it all together. Okay, so let's do as said and take the derivative. So what is f prime of x? We get 12x squared minus 8x cubed. And then when you set these equal to 0, you always want to factor. Okay, so let's go ahead and factor this. We can factor out a 4x squared, and we're left with 3 minus 2x equals 0. Okay, so we have x equals 0 to solve, and x equals, if plus 3, it would be 3/2. Okay, so what we're going to do is make this little graph to get further information about what types of points these critical points are. Okay, so we've got the point 0 and 3/2. Okay, so we look to the right of 3/2, and let's take the point 4. If you plug in, or 2, it doesn't matter. If you plug in 4 here, you're going to get a negative times a positive is a negative. If you take the point 1, positive times positive is positive. If you take the point -1, this will be positive, and this will also be positive. Okay, so this gives us great information about the graph. What this tells us is that 3/2 is the only minimum or maximum. And because the derivative is going from positive to negative, it appears to be a maximum. Okay, now we're going to do the second derivative to get all points of inflection. So let's do f double prime of x, see what we get. Okay, so we get 24x minus 24x squared. That's interesting. So how do we deal with that? Well, we can factor out a 24x. And so we can say 24x, and then we'll be left with 1 minus x equals 0. And so we can see that we do get 2 points of inflection here. Okay, I'm going to label these f prime, and this is f double prime. And we get 0 and 1. Okay, 2 points of inflection. Now let's see how the concavity changes between these points. Okay, so if x is positive, say 2 positive times positive, it's positive. Now, what about 1/2? Okay, the number doesn't matter, the sign is what matters. Okay, so now wait a minute. So it's getting 2 positives in a row that helped me realize I made a mistake. If you plug in 2, because the expectation is that the concavity will change. Okay, and these are intervals, so they really keep going. So if you plug in a 2, that's a -1. Negative times a positive is a negative. 1/2. Positive times positive is positive. Now what about like -1? Positive times negative is negative. And so this is how the concavity changes. Okay, so let's put these pieces together now, just these ones, in a graph, and see what we end up with. Okay, so let's do it something like this. Okay, so our critical points here are x equals 0. Now let's make this a little large so we can fit in everything. 1 and 3/2. Okay, and we figured out that 3/2 is in fact a maximum. Now we don't know if it's down here or up here at this point. You can sort of look at the original to try to figure out what it should be. Not easy to plug in 3/2. We could try. Let's just assume for now that it is somewhere up here. Okay, and so these other points are in fact points of inflection. Okay, and so recall a point of inflection is kind of like this one where the concavity is shifting. So what's happening at this point is it's going down, right? The graph is going down, and it is going to shift when it reaches this point. Now we don't know where it's going to hit that point, but that one we can more easily plug in because it's a value of 1, right? And like, what is the value of 1 in this original? Well, it's simply 4 minus 2, it's 2. So, it's not really drawn to scale here, but if it's at 2, it's going to be more like up here, right? And then we can easily plug in 0. We know that this point should be 0. Okay, so we've got points here, and this point is going to be above it somewhere. Why do I know it's above it? Because it's a maximum, okay? So what's going to happen, it's going to go down, okay? It is concave down, but what happens here is going to switch to concave up, okay? So like what we have here, is a flip. So this one's going to be more like, if I can draw it right, move that one out of the way. Okay, so we got a point here and here. And so it is a switch of concavity at that point. So we've got it going concave down, and now it becomes concave up, okay? You see how that switches? And so now when you go concave up, now this is more like this one because it's going from concave up to concave down. Okay, and so this is what we should end up with. Now, because this is in fact a maximum point, right, it's got to actually go down. And so it goes down something like this. And you could find the point where it intersects where y equals 0. You could factor and figure it out. And so I'm just going to draw it like that for now. So that is basically one example of how you can use calculus to sort of help you figure out the critical changes of a given curve. I want to do one final really cool example, and this is a trig one. Let's take f of x equals x minus cosine of x. And we're just going to start this like we usually do. Let's take the derivative and look at the critical points. Okay, so f prime of x equals 1. Now, derivative of cosine is negative sine, so this will be a plus sine of x. And we want to set it equal to 0, and that is when sine of x equals negative 1. So when does the sine of x equal negative 1? Well, if you think of the unit circle, okay, that's actually when cosine is negative. When sine is the y value. So the sine is going to be negative 1 down here, right? And that's when x equals, what is that? That's like, it's going to happen when it's like 3 pi over 2, right? And then it's going to be all of those, all the 3 pi over 2s. Now, it's not pi over 2. Right, pi over 2 is positive 1, so we're going to get 3 pi over 2, not pi over 2, so I think the next one would be like 7 pi over 2, and then and so on. And then the negatives 2 in that direction, so we will get like negative pi over 2. Because I guess we should count those two. Okay, so let's plot these and see what happens in between. Okay, so we're looking at, we'll go with the negative pi over 2, 3 pi over 2, 7 pi over 2. Now these would commonly be restricted on a certain interval, but let's just get a feel for it by looking at the whole thing. Okay, so what we want to know is how does the derivative change in these different values. So what can we start with? Let's start with 0 because that's the easiest to compute. Sine of 0 is 0, we're looking right here. Okay, 1 plus 0 is 1, this is positive. Great. Now let's come over here. That 4 pi over 2 is in there, so that's like 2 pi. Well, the sine of 2 pi is 0. 0 plus 1 is 1, that's positive. What about over here? We take negative pi, also 0, positive. Wait a minute. Up here we get to 4 pi, all positive. What's going on? This basically shows us that the sine, because the derivative is always positive, the function's always increasing. Interesting. Okay, what about the second derivatives? Okay, well, we got to compute them. So now we're here, derivative of sine is just cosine. So we get cosine x, and we want to set that equal to 0. Okay, well, when does the cosine of x equal 0? This is when the x value is 0, and it's going to be it's going to be these values, but also the ones above it. okay? So we've got x equals 0 at, it's all the pi over 2's. So it'd be like negative pi over 2, for instance, plus or minus pi over 2. We get them an interval speed, 3 pi over 2. A lot of ways to write these. Dot, dot, dot. It's really dots in both directions, right? Because it's also the negatives. And same with this one. Okay, so let's find out now what's going to happen with these critical points. These potential inflection points, right? The inflection points. And we've got, let's just start with negative pi over 2, pi over 2, and we'll go with 3 pi over 2. Okay, again, we'll start with the easiest one, 0 in the middle. It's just right here, it's cosine. So it's cosine of 0 is 1, this is positive. Okay, now what's the cosine of pi? Cosine of pi is negative, okay? You keep coming around, right? And then you get, because to check the next point, you'd be checking like 2 pi, you're back where you start, positive. And certainly like if you take negative pi, right? Positive, negative pi gives you the same thing, cosine's negative there. And so these are all points of inflection, okay? So what the heck does this graph look like? Let's attempt to draw it. Now, when we do this, it's good to have a value, right? Like 0. What is the function at 0? It's 0 minus cosine of 0 is 1. It's negative 1. Okay, so there's a point. Now, our next our critical points around that are the negative pi over 2 and pi over 2. And so it's hard to say exactly what it is. Okay, so the cosine of pi over 2, here, let's put it up, pi over 2. Now, what's the y value here? Well, it's basically the cosine of pi over 2 is 0. It's actually just pi over 2. So it's going to be sort of symmetric. Right, and negative pi over 2. If you put in cosine of negative pi over 2, well, wait a minute, those are all zeros, it's going to be negative pi over 2. Okay, so you get this symmetry going on that should continue. And so what happens? What happens is, let's do it using the calculus, let's try. So you've got these points of inflection, and if we start, like, let's look at the negative pi over 2 to pi over 2, it's concave up, okay? Is that right? Negative pi, yeah. Concave up. Okay, so basically, hard to draw, right? It's because it looks like it's a straight line, but we somehow want to make it like concave up, and then what's going to happen is it's going to switch to concave down. Okay, so it switches to concave down, concave up, and as it keeps going, it switches to concave down once again at like negative 3 pi over 2. And so what you end up with is you end up with sort of a curvy function where this pattern in effect continues throughout the whole graph. That's just a rough sketch because it's difficult to draw, but it is really, you can imagine, you know how cosine is like squiggly, right? It's like a wave. It does the wave pattern over x. Okay, so it's really cool kind of looking. You can see how we can kind of use calculus to really help us graph it.